Welcome to the very first episode in this series. If you don't know what I'm talking about, here's a quick rundown. I'm basically going to reteach Leonard Susskind's and Art Friedman's book on quantum mechanics. You don't need the book to follow along. I'll provide context for everything, and we can have discussions in the comment sections later. Oh, and since I'm a strong believer in education for all, I'll link a PDF of the notes I took while reading this book. I'll focus on the actual material while another YouTuber focuses on the applicable side of them. There'll be more on that at the end of the video. For now, we'll get started. I'd like to start off by saying that quantum mechanics is weird. It's confusing, unsettling, and you're either lying or not listening if you still think it isn't even after you watch this video. See, our minds can't possibly understand quantum mechanics, and it's not entirely because of rigorous math or dizzying abstractions. It's because everything happens at a scale so small that we can't process it. It's just way too different from what we expect from our classical perspective of the world. Mainly, there are two differences in the quantum world and our own, the classical world. The first one is abstractions. The reason they're different is because the quantum world relies on entirely different logic and mathematical objects. The second one is states and measurements. They're two separate things, but they're also somehow intertwined with each other. Now, it's completely alright if you don't understand what I just said. Actually, it's even better, because if you're new to quantum mechanics, I can guarantee you that whatever you think I just said is wrong. Anyways, it's alright if you don't understand what I said, because that's the goal of this video, to introduce you to these differences. To get to know them, we'll have to deal a lot with spin, and spin will show up a lot in this series. More specifically, the spin of an electron, but be warned, it's not an actual electron spinning. I highly recommend you watch Looking Glass Universe's video on spin. It's very informative and gives some good background knowledge. That way you won't get confused as easily. I'll put the link in the description, go ahead and check it out. I'll wait. If you're still too lazy, the best explanation I can give you is that it's an unknown force that gives particles magnet-like properties. The book calls it a degree of freedom, which I think is just vague enough to not get us confused. To continue with the degree of freedom explanation, and to make further explanations a little more relatable, we'll represent the spin of a particle as an arrow. Note that this is a terrible analogy, and people who watched Looking Glass Universe's video will understand why. The spin is the simplest quantum system there is, and by itself it's called a qubit, from quantum bits. You might recognize bits as the ones and zeros in binary, and you'd be right. Quantum bits are a type of logic, like binary logic, except with a new quantum dimension added to it. Understanding how this logic works will help us grasp the concept better. So let's toy around with systems for a bit. Let's start by taking a look at the simplest one, a two-state system. It's represented by a bit or something that can have only two possible values, like a 1 or 0, true or false, or on or off. In physics terminology, this is called inventing a degree of freedom, named sigma, that can have two values, 1 or -1. Why we chose those numbers specifically will become apparent later on. Oh, and I'm not going to say sigma over and over again. So from now on, I'm going to call it O. We can measure O, and it'll yield a result of either 1 or -1. However, these states can evolve or change from measurement to measurement. And it's not hectic, not yet at least. There are laws that the evolution follows, with the simplest of them being nothing. The measurement doesn't change at all. And it's written out like this. We can measure all we want, but we'd be overlooking one extremely important aspect, the apparatus that measures it. Normally, we can assume that it functions perfectly in every way and that it wouldn't really be necessary to factor it in. But trust me, adding it will play a big role in understanding the difference between quantum and classical mechanics. Some basics of the apparatus is that it's perfect. It has this side up arrow to help us know its orientation in space, and we don't know the measurement before it measures it. Now, we can start experimenting with the apparatus. For our first experiment, we'll test out the simple evolution law I just mentioned. Let's measure O, and let's say it yields a -1. Next, we'll reset the apparatus and measure O again. According to the simple evolution law, it should be the same as our last measurement. And in fact, it is. This will be called experiment A. In experiment B, we'll do something a little different by manipulating the apparatus. We'll start off just like we did in experiment A, and let's say it yields a 1. Now we'll reset the apparatus and turn it upside down. Once we measure the spin again, it yields a -1. This is pretty intuitive because instead of measuring the z component of the spin, we were measuring the negative z component. It's kind of like asking which way an arrow is pointing. If you were upright, you'd say that this arrow is pointing up. If you were upside down, you'd say that the arrow is pointing down. This is, of course, assuming that you didn't experience gravity or have any contact with the outside world. Keep in mind that when actual scientists did experiments A and B, they didn't have the concept of spin sorted out at all. So it is natural for them to assume that spin was a vector with a certain orientation in space. And it should seem natural for us as well. At this point, you may even wonder what the difference between classical and quantum mechanics is, because everything we've done so far seems to be intuitive in a sense and in line with classical mechanics. Well, this is where it starts diverging. Assuming that spin is a vector with a certain orientation in space, let's start a new experiment called Experiment C. Once again, we'll measure O, and let's say we get a 1. Now, we'll reset the apparatus and turn it sideways. Now, what do you think will be the result when we measure O again? Take a moment to pause the video and figure it out for yourself. It's a little hard to understand with the apparatus, but you get a clearer image when you use the arrow direction example I gave earlier. So let's use that as an analogy. When we turn you sideways with an arrow pointing in the z direction, you might be tempted to say that it is indeed pointing to the right. But you have to remember, your only job is to decide if it's pointing up or down, and not anywhere else, because there's only two possible states. In classical mechanics, the outcome should be 0, because there's no up or down component for you to measure at all. But what actually happens is that you guess, or more formally, there's a 50% chance that the spin is a 1, and a 50% chance that the spin is a negative 1, and it averages out to be 0. What's really happening will become even clearer when we started at an arbitrary angle and use vectors. We can see that vector m is kind of going towards vector n, and if we reflect m onto n, which is the same thing as taking the cross product or cosine of the angles, we essentially get the n component of m. And that component will be the average, not the outcome of all the spins. So if the cross product of m and n is 0.47, then once rotated onto vector n, it would have a 74% chance of being a 1 and a 26% chance of being a negative 1. You can either take my word for that example, or try to work it out yourself to see how well you've grasped this concept. I want to present to you one more experiment. I promise, this is the last one. We'll follow the steps of Experiment C, but once we measure O on the x-axis, let's turn it back over on the z-axis. When we measure the z component, one might expect it to be what we initially measured, which was negative 1 by the way, because of the simple evolution law. But no, it's completely randomized. We lost all the information about the z component because we measured the x component. You see, in the quantum world, there's no way we can know everything about two different components at the same time. And to know one component, we have to destroy information about the other. The key rule here is that any interaction strong enough to measure some part of the system is strong enough to disrupt another. What we just covered with all the experiments and states was mainly talking about the states and measurements difference in quantum mechanics. Now I'll introduce you to the logical differences in quantum mechanics. Remember when I talked about systems and how the simplest system consisted of two states? Well, those states can be arranged into a space of states, which is a mathematical set that looks something like this. A die space of states would look like this with all of its values listed. A coins would look like this with all of its possible values listed. We can have a space of states for spin as well, and it would be represented like this. To make sense of the logical side of the states of spin, we would use Boolean logic. It consists of things like and, or, and not functions, and is always either true or false, and nothing in between. I'll expect that you already know these, and if you don't, just do a quick search. It can't be more than a few clicks away. We'll test two propositions of two different statements. Statement A is, the z component of O is equal to 1, and statement B is, the x component of O is equal to positive 1. The two propositions are A or B, and A and B. One key thing to help us understand what's happening behind the scenes is to have an unknown agent that automatically sets the spin of the z component of O to positive 1. To test these, we have to utilize our apparatus again. For the first proposition, we start off by testing A, which will always be true because our unknown agent set it up that way. And it doesn't matter if B is true or false because A is already true. Let's try the same proposition in reverse. First, the unknown agent sets the z component of O to positive 1. Then we measure the x component of O, and if it comes out to be positive 1, the proposition will always be true. But for the sake of this video, let's say it comes out to be negative 1. Now, since the first half is false, we'll test out the second half. Before we see the outcome, let's reflect on what happened in experiment D. Because of measuring one aspect, we destroyed another. And this is exactly what's going to happen here. Whatever the unknown agent set for us will be destroyed because we tried to know another component. Therefore, there's a 1 in 4 chance that this proposition turns out to be false. The important thing that this proposition highlights for us is that quantum propositions aren't symmetrical. We can see that because the first proposition had a 100% chance of being true, but when we reversed it, there's a 1 in 4 chance that this proposition could have been false. The second proposition is a little strange. We can follow the steps to test if this proposition is true. and there will be a 1 in 4 chance. But even though we follow through with this proposition, we need to be able to retest it for confirmation. But this would be impossible because they'd be completely randomized after measuring other components. So this entire proposition is just invalid. Not wrong, just invalid. Some might recognize this as a Heisenberg's uncertainty principle. If you don't, that's alright. It basically says that a particle can have two components, position and momentum, though it can apply to any measurable pairs. One example is the components of a particle spin. Having position and momentum at the same time makes no sense at all, and having position or momentum means something that I bet you aren't thinking of. This is an introduction into the weirdness of quantum mechanics. We'll dive deeper into this soon, but it'll take some knowledge of complex numbers and some vector notation. So that's what the next video is going to focus on. I hope that you were able to notice and understand the differences and where they came from. If you didn't get everything, try reading the notes, or rewatching the videos, or even rewatching the videos with the notes. And please do comment any doubts you have. I'll start some discussions as well to help you guys start thinking more about this. It'd be great if we can have at least 10 comments sharing and helping each other out. Oh, and the other YouTuber, as I was writing the script, he hasn't made his channel yet, but as soon as he does, I'll put a link in the description telling you to check it out. It'll be great. You guys will use what you learned in this video and apply it to things in the real world. He should have a video out next week, that way you guys are alternating between learning and applying every week.